So everybody tried this 3 degrees of freedom model to set up the equation of motion by applying the free body diagram around each mass. Then you have 3 coupled equations of motion. Then you can cast into the matrix using matrix notation. Really, you did? Did? So, simple Newton's second law, and to catch the concept. So that's what I want you to do. And this is mass matrix. Mass matrix. This is really lumped mass matrix. There are 2 different kinds of the mass matrix. One is the lumped mass matrix. Another type is consistent mass matrix. Old days, we were using 2 different methodology to generate this matrix notation of equations of motion and the approach for formulation for mass matrix. But after the computer power is really great, then the lumped mass matrix is very popular. But in this case, this is really discrete mass, 3 lumped mass there. So always you will have the diagonal mass matrix. And any commercial code, Dynacode, Nastran, ANSYS, Abacus, is all dealing with the diagonal mass matrix, which makes computation a lot easier. So that's what the convenient is. And this is a diagonal matrix, means there is no coupling here in the mass. By looking at the matrix, this is a square matrix. In this case, it's a 3 by 3 matrix. Of diagonal term is equal to 0, and no coupling between the coordinates. But as you look at the stiffness and the damping matrix, this is not the diagonal matrix, but off diagonal term is non-zero. This is off diagonal term. You can say x1, x2, x3, x1, x2, x3, and x1, x2. x2 is coupled with 1, 2. I'm sorry, 1. This element is x1, x1, x2. So this is a C2 will couple between the x1 and x2, as you see here. As you see here. As you see here, x1 and x2, between there is a C2. The C2 and the K2 couples between x1 and x2. So in the matrix, there is a non-zero term right in x1 row, x2 row. In that situation, but there is no coupling between x1 and x3. So what that means, the x1 row, the element in x1 row and the x3 column is equal to 0, because no coupling there. So as you see here, that's what you see, that this is 0. 1, 2, 3, x1, x3, no coupling. Or 3, 1, same thing. This is a symmetric matrix. So as you see here, these two are coupled off diagonal term. Okay? So C3 or K3 makes a system couple, because this one K3 is a spring between X2 and X3. So this is a couple, right? So that's this makes the system couples. So M, C, and K. And this is a response vector. So its X is X1, X2, X3. In this case, X1 is not only the displacement, in that horizontal direction. So you can say X1 degree of freedom, X2 degree of freedom, X3 degree of freedom. Okay? So, of course, this X is unknown. So it's a vector. So linear transformation. Remember, I introduce here is M X double dot plus C X dot plus Kx is equal to 0, because this is 0, because we are dealing with the free vibration problem. So it's a modal analysis. So damping is involved here in general expression. But whether there's a damping or no damping, mode shape is concerned as same. So damping introduced the energy dissipation in the system. And damping effect is usually in structure dynamics is very small. So I mentioned in terms of the zeta, the damping ratio, zeta value is, for design purposes, about 2%. Okay? That's not the really material damping. It comes from the build-up structure like a joint in the system. So if I delete the damping in the system, then it's going to be like M X double dot Kx is equal to 0. And then you can use to determine the so-called mode shape from that undamped system equations. Please do. In my past years of works, I had a chance at the beginning, of course, to solve the damped system, to determine the mode and damp the natural frequencies and all that. But really damp the natural frequency or undamp the natural frequencies, small fraction of 1 hertz, even less, are difference. So you don't have to really calculate the damped natural frequency. For the single degree of freedom system, as I recall, this is, let's say, undamped natural frequency, and damped natural frequency is Fn times minus, this is, I'm not sure whether there is a 2 or not. I'm not sure, but factor of 2 could be. 정원, you remember? In this? Anyway, so here zeta is, I'm talking about 0.02, right? 2% damping. So 2% damping is, if you square it, is going to be what? 0.0002? Correct? Or 0.0004? Something like that. So 1 minus 0.0004 is very close to 1. Square root of the value which is very close to 1 is about to 1. So this result for small damping is about the same. You see it? So that's another reason you can just use undamped system to compute natural frequencies. Mode shape wise is a shape. Mode shape does not tie down with the dimension. So like a 3 degrees of freedom system, the first mode, intuition first, okay? First mode is usually in phase, acted together. And the second mode is out of phase. So like a 2 mass may be acted together. Then third mass is out of phase, like this. And another mode will be the other 2 mass kind of in phase. The other one is out of phase. So something like this. So then of course three natural frequencies. And here is a linear transformation. This linear transformation is the process to move the system from physical space into the modal space. Whoever did not have a vibration background kind of maybe uncomfortable, but it's very straightforward. The things, as it said, is a linear transformation. Then we're going to say let x is a physical coordinate in the physical space. This eta is a modal coordinate, or some people call generalized coordinate. So eta, so is a let x is just a let, and the phi which is time domain function. This is time domain function. So this is called the modal coordinate vector, I can say vector, and or generalized coordinate vector. It's a name. But the physical space is defined right here in xt. Then you throw into the modal space. Right here is all connected together. System is connected. But here, the system is not connected. It's all independent each other. So I can say this is eta 1, this is eta 2, this is eta 3. It makes a big difference. Here in this case, this is x1, x2, x3. You know what I'm trying to say. Put that in the modal space. So this is a physical space. This is a modal space. And here is what the transformation matrix is, a phi, which is called the mode shape matrix. So over here, this is mode shape. Whoever didn't take the vibration or took the vibration long time ago, then this is a good time to review, just to refresh your mind. Whoever didn't take such a course, this is the time to learn. There is no more than this, no less than this. This is it. Okay? It's a mode shape matrix. Sometimes in mathematics, this is called eigenvector, eigenmatrix, I'm sorry. Eigenmatrix. Just to learn the name for a while. Then this phi is consisted of the phi 1, phi 2. In this case, 3 degree of freedom system has phi 3. That's all. This is a vector. First modal vector, second modal vector, third modal vector. Put the whole thing together, then that's called the modal matrix. Or some people call mode shape matrix, vice versa. So we're gonna say all I have done here for linear transformation or the modal transformation, same thing. I say let x is equal to phi matrix times eta. Okay, just say let. Okay. Then of course, if you take a time derivative, velocity vector, eta dot, time derivative, double dot, acceleration, eta double dot, time derivative. Then after that, what I did here is multiply. Simply multiply. So I'm going to replace this guy into here, this guy into there. That's all I'm doing here. If I do that, what I have is mass is still there. X double dot is phi eta double dot, which is a function of time t, plus k phi eta, which is a t, is equal to 0. Then what I do is I pre-multiply phi transpose. I'm going to pre-multiply phi transpose. I'm going to pre-multiply phi transpose. I'm sorry. This is equal to 0, right? We are dealing with the 3 degrees of freedom model, but if we are dealing n different mass, n. So this is gonna be n by n matrix size, right? And this is gonna be phi. Each column there is n number of row. So this is gonna be n by 1, n by n. This is gonna be n by 1. The resultant would be what? N by 1. Oh, I'm sorry, here we have to have phi transpose, the phi is n by n, so when you take a transpose, what size is that? Same size, n by n. So this is gonna be n by n. If you multiply all the way, which you will have n by 1. Or, in the eta, I'm going to leave this guy out to show the equation in the modal space. If you do that, this is going to be n by n. And this is going to be what? N by n. This is going to be 0, n by 1. Make sense? And this, I'm going to call this guy as m tilde, m bar. I'm going to call this guy as k bar. This is right hand side is equal to 0. That's what this is. K, this is a bar. Okay, this is m bar. So shown down there is what that exact notation is. And just showing this class for covering about maximum 2 hours for modal analysis. And this M is a diagonal matrix. This phi is a full matrix because each column is a mode. Okay, so when you have this phi transpose M phi and the phi transpose K phi, there is a particular modal characteristics. This is not the diagonal. It's off. There is a non-zero off diagonal. When you do this operation, this becomes the diagonal matrix. That's a modal characteristics. I'm not sure whether I have an area to discuss about the detail. So regardless, this is beginning of modal analysis. So this is, so I'm going to put that kind of the notation to say that that's a diagonal matrix. In what space? If I rewrite this, this is going to be M bar eta double dot plus this is a diagonal and the K bar diagonal eta is equal to 0. Diagonal and diagonal in what space? Eta space, modal space. Diagonal means off diagonal terms are equal to 0, which means there is no coupling among the degree of freedom or modal coordinate. Modal coordinates are all independent each other. So here, if you do that, if I take ith row, okay? If I take ith row, just ith row. Oh, I'm not this one. I have to use this. I'm taking the ith row. So if I take ith row, mi I, and this eta I double dot t. I'm just rewriting this, the matrix kind of the notation into the one particular row called the ith row. Plus this one is Kii, eta I, of course a function of time t, is equal to 0. I is equal to 1, 2, all the way through n in general. In this example, it's going to be simply n is equal to 3. Look like I'm going a longer way. But here, this is, if I take just the one first row, which means M11, eta 1 double dot plus K11, eta 1 is equal to 0 when I is equal to 1. That's like this case. Just it's like a single degree of freedom model. It has nothing to do eta 2, nothing to do with eta 3. So that's one of the reasons to throw the model or system from the physical space into the modal space. Then life is easier. It's very easy to solve. This equation is the second order, the ordinary differential equation. You did it already, very easy to solve. And this is only the homogeneous solution is what you need, no particular solution, because it's a free vibration. So here, one step further, if you divide it by M11, M11 in our model is equal to M1 in our 3 degree of freedom model. So eta 1 divided by M11 plus K11 over M11, this is equal to really K1 over, well, you can say like this, I'm going to leave as is, which is equal to omega 1 n1 square. First natural frequency square is K11 over M1, M11. You can see this is really K1 over M1. Okay? So this is equal to eta 1 equal to 0. You can solve a homogeneous solution, which is A sine omega n1t plus B cosine omega n1t. So that's what. So doing this here, I can write as in general I plus omega ni square eta I is equal to 0. Over here I is equal to 1, 2, all the way through n. Is it all understandable? Logics, flows, reasonings, and all that. And of course, if you put it all together, it's eta double dot plus omega square. This is really put this all together into matrix form. This eta square, the omega square is a diagonal matrix here, which is omega n1 square, omega n2 square, all the way through omega nn square. All others are 0. Diagonal matrix, omega ni is equal to what? Circular natural frequency of the system. Got it? Very straightforward. And you pull out the one, ith row, then you have this. Simple, the second order differential equation in what space? 처럼? Modal space. So over here, where is the eigenvector, eigenmatrix? I said that this is eigenmatrix, phi, right? This is phi. This is eigenmatrix. So over here, this is like eigenvalue, in this case matrix, but omega, each one, omega ni square. This is really called the lambda. Usually in math, when you solve eigenvalue problem, so this lambda is called eigenvalue of the system. Eigenvalue. So conduct the modal analysis in engineering means in mathematics, solve eigenvalue problem to get the eigenvalue and eigenvector. So each if you put it all, the eigenvector, then that's eigenmatrix, something like this. And just as in section C, really again rewrite the equation of motion in matrix form, or you can just expand it, then you will have m times x double dot is summation about the j, right? J is each row of x double dot, you can say, and this is expansion form. Now solve the eigenvalue problem. So I'm just showing here the process. There are many different approach to solve eigenvalue problem, efficient way, but in this case it's very straight way to show the basic logics. So first I'm going to say let x is equal to phi times eta, one particular eigenvector. Capital phi matrix is put all the eigenvectors together to make a matrix. Each row, each column is eigenvector, right? So I'm going to say let x is equal to phi eigenvector times eta modal coordinate. Then if I take ith row, which is xi is equal to phi I eta, I just pick out ith row. Then if you take a derivative twice, then you have that. Then plug back into this expression into here, then it's going to be m times eta, m times the phi times the eta double dot, and do the same thing over here. Then you have this, or expanded forms like this. So now here comes here. This omega d is damped for the damped natural frequency. It related to undamped natural frequency times the square root of 1 minus eta square, not the 2, okay? Happen to be eta square. Eta is what the nominal damping ratio you are dealing with all the time. So this is expanded forms, okay? So using the expanded form, you can move one term to the other side and you can take the ratio. Is it clear? This expression is identical to this expression. Take the one term to the other side and divide by eta double dot by eta. Then you have this. This happens to be equal to this. But first term, this is time dependent, right? This is equal to time independent. So time dependent ratio is equal to time independent ratio. What that means, to qualify to be valid, this has to be the constant. Otherwise, it's not going to work. So, okay, this is a constant. So now this is equal to the lambda. So if you said this is equal to lambda, then I can write this here. Is it clear? And the second term, this expression is equal to lambda. This lambda is called the eigenvalue. This lambda is eigenvalue. Okay? So this is, just rewrite this. This is equal to lambda. You have this. Okay? You have this. So now we have to solve this. And I'm going to say to solve this, this is piece of cake. Because this is second order, simplest second order ordinary differential equations here. Eta double dot. So I'm going to say assume or let eta is equal to a times e to the st. So e to the st, s is the root. For at least half of you, this is a good review, isn't it? I think most of you I can see is a very good review. So eta double dot plus lambda eta. Of course, this is a function of time t is equal to 0. So then we're going to say let or assume eta is equal to a times e to the st. Okay? Then what we do? Then substitute this guy into the second order the equations. Then you have, if you plug in, so you have, if you plug into here, eta dot is equal to a s e to the st, eta double dot a s square e to the st. If you plug in over there, which is as square e to the st plus the lambda a e to the st is equal to 0. So then I'm going to take a out, e to the st out, and s square plus lambda. Oh, missing is here is s, right? S, right? Oh, I'm sorry. There is no s here. There is no s here. Lambda is equal to 0, right? But this is not equal to 0. Then this has to be equal to 0. So that's what get down here, then you can move this around here. A has to be all cancelled out. So over here, S is equal to plus or minus square root of minus lambda. So which is equal to plus or minus square root minus complex number I. Lambda right here, I'm going to say lambda is equal to omega square. So which is equal to omega. So root is concerned, S1 is equal to plus I omega, S2 is equal to minus I omega, root. That's what the root is. So this lambda is called what? Eigen. Lambda is called eigenvalue. Natural frequency square. Natural frequency square. So now to get the solution phase, so we're going to say eta is equal to A1 constant e to the minus e to the I omega t plus A2 another constant, because it has two roots, plus or minus. So e to the exp is e to the minus I omega t. I omega t is sine and cosine, right? E to the I omega t is equal to, and which is cosine omega t, sine or cosine, plus I sine omega t. E to the minus I omega t is cosine omega t minus I sine omega t. I think order, check it, I think it should be correct. It's a sine cosine, so you can, which is really function of sine cosine. So if you do that, then what you have here is this expression is sine and cosine, sine and cosine. So in general, I can put it out saying sine omega t plus cosine omega t with the constant A1, A2. Or sine cosine has a phase difference. So two unknowns, you can have that expression which has how many unknown? Two unknown, C and phi, amplitude and the phase difference. You can express, so any form is all acceptable. So so that's the general expression. So I can say over here, for displacement vector, I can write in general, x is equal to the phi, which is eigenvector, times cosine omega t minus theta. Okay. This is in the matrix, the notation for equations of motions. I can rewrite this guy into as minus omega square plus k, the phi, which is coming from over here. Okay, expanded form. This is expanded form. You can put that into that form. So so you got from here you get the solution for eigenvalue. Then from here from this equation, to qualify to have a solution, the determinant of this term has to be equal to 0. Otherwise, no solution, because right-hand side is equal to 0. So determinant, this is a determinant, has to be equal to 0. So this is n by n, determinant, matrix of the determinant is n by n. So then this is going to be, if you expand it, that's going to be nth order of polynomial of lambda. So how many roots you're supposed to have? N different roots in general. But if there is a chance to have same roots, two eigenvalue could be the same in some situations. For example, you have a CD. At the center you have a hole. So if you look at the mode shapes and the corresponding natural frequency, whether you put this guy, this is CD, this way or this way, frequencies are the same. Mode shape is the same. So some situation, the natural frequency could be same between the two modes. So that is exact example. Round CD, mode gonna be like this, so mode gonna be is all same. That particular mode is identical mode situations. You could have that. I think I have some comments in down here. And n different in general, n different natural frequencies or eigenvalue, then always you list out the smallest eigenvalue first, or natural frequency first. Lambda 1 or omega n1 first, all the way to the highest. So of course you will have a chance to solve 2 degrees of freedom system. If it's a 3, what's the polynomial equation? It's a third order polynomial equations to solve. Can you solve by hand easily? Not easy. Even 3 degrees of freedom model, not easy to solve natural frequency, because you are talking about solving the cubic equation. Of course you can. By hand it takes a much longer time, but usually you can write in your even phone. Maybe you have a you have a calculator, programmable calculator. You can solve for that. Okay, so 2 degrees of freedom, which will provide the 2 eigenvalues and eigenvectors, you can very easily to solve, to capture the process of to solve. So that's what you can practice here. So you have examples, even 2 degrees of freedom model, which need some work to do. Then capture and understand the process. So you have, in this case in general, you have n natural frequencies and corresponding modal shape. Still it doesn't ring the bell for maybe some of you. So when we solve 2 degrees of freedom model, then everything will be very clear. Then we'll normalize it. Then we'll do some work. So for the every lambda, every mode, every eigenvalue, then we have to find the corresponding eigenvector or mode shape vector. using this is where it come from. It come from right here. Right, that one. Or this is equivalent to this. Put back into matrix forms. For this one, back into matrix form. That's what this is. Identical. So this is a very general, or this very general expression to solve the eigenvalue. So this is a very typical eigenvalue problem set. So here, so phi related to first mode all the way to n mode. So in this case, R is equal to 1, 2, 3 all the way to n. Okay? It's a mode shape is equal to the degree, number of degrees of freedom system. So K phi rth mode, omega r squared times m phi r. So again, as I write some comment here, omega r is rth, the modal frequency or natural frequency, and phi r is the corresponding rth mode shape vector. If phi r is a solution, this is a mode shape. Shape is important. So like the M1, this is M2, which has x1, x2. Really how many inches in first coordinate move is not important. Relative ratio of displacement is important. Because mode shape relate to, let's say, displacement, amount of the displacement is not important. So you have a mass there, you have a mass there, you have a mass there. So if this guy move here, this guy move here, this is M1, M2. So mode shape, if this guy move here, the value of 1, this guy could move the value of 2. So ratio is 2 over 1, 2 over 1. But I can say this guy move 2, then this guy will move 4. It's identical. Ratio is concerned 4 to 2, which is 2, this is 2. Ratio is important. Amount doesn't mean anything for the mode shape, because it's simply showing the shape. You can think that way. And so if phi r is a solution, then alpha r, some constant, any constant, times phi r is also a solution. This implies that the mode shape is unique, not the amplitude. Make sense? That's what the mode shape is. But not natural frequency, not eigenvalue. Eigenvalue is very unique. So overall solution is concerned, x is equal to phi times eta, or phi times c, constant. C is any constant, times cosine omega nt. C and theta are two unknown, which can be solved by initial conditions here. So for the rth mode, xr, phi r, cr, omega r, phi r, we have a total n number of mode. So to get the total solution, you have to apply the principle of superposition. So this is applying the principle of superposition. Okay, so I'm going to stop right here.